Okay, we're going to carry on with the chapter on bipolar junction transistors. Today we're going to discuss BJT characteristics and parameters. So let's refer back to the textbook and read the introductory paragraph and see what we're going to learn in this section. Two important parameters, beta DC, that's called the DC current gain, and alpha DC are introduced and used to analyze a Bjt circuit. Also, transistor characteristic curves are covered, and you will learn how a Bjt's operation can be determined from these curves. Finally, maximum ratings of a Bjt are discussed. Okay, so if we turn the page and we go and look at the first figure, that figure should look familiar. We've discussed it in the previous section, in the previous lesson, where we've seen I have to bias the transistor if I want to use it as an amplifier. So we basically have here are the transistor DC bias circuits that we've seen in the previous section. Alright, so again, the NPN and the PNP are discussed. In the case of the NPN, which is mostly discussed, but we've also seen that the PNP is the same, only that the current flows in the opposite direction. Alright, then I've got two supplies in this case. It will not always be the case, but we will learn more about it later. I've got a VBB, which will bias my base emitter junction. Remember, the base emitter junction should be forward biased, so I'm looking at that series circuit, and I should have a voltage drop over the base emitter junction of approximately 0.7 volts. Approximately, because remember, you've done the diode and you've seen in the lab that the voltage is not actually 0.7, that's an average that we take, but for all our calculations we will use this approximation. Alright, I have another supply which is called VCC, which will let the current flow in that direction for IC, and I can see that my base collector junction should now be reverse biased, and I have my forward reverse bias condition as I should have for a biased amplifier circuit. Alright, then the currents, as I can see, IC, IB and IE. And we've also learned that IE is the largest because IE is equal to IC plus IB. And the same applies to the PNP transistor as well. Alright, firstly, what we're going to look at then is the DC beta and the DC alpha. If we can refer back to our textbooks there. Now you can underline this. These are ratios that we're going to use. Remember, we've seen in the previous section that the transistor is actually a current amplifier because of the way that the transistor is constructed, and of course the way that the materials are doped and the size of the materials and so forth. Okay, so the first one there, you can underline the DC current gain. The DC current gain, remember I said this is actually a current amplifier of a transistor, is the ratio of the DC collector current to the DC base current, and is designated as in equation 4.2. So beta DC, keep in mind that the capital letter subscripts indicate that it is a DC quantity, is equal to IC divided by IB, all DC quantities. You can underline the following as well. It says typical values of beta DC range from less than 20 to 200 or higher. I think the transistors that you are issued in the, or will be issued in the lab to work with, have a beta of 350 to 400. But we will talk more detail about beta. But what I can see is that the value of beta DC is normally a large value. Why is it a large value? I can check it. What have I learned about the currents? I've learned that IE is the largest current because it adds IB and IC. But when we've discussed the operation of A transistor actually, what happens, how does it amplify, what we've seen? Emitter, highly doped, big, base material, thin, lightly doped. Okay, so what's going to happen? Little bit of recombination. So what can I see? The current of IB is very small in comparison with either the collector current and the emitter current. But I can see that the emitter current is the largest, so it will be, by the magnitude of IB, it will be larger than IC. But actually, IB is so small, in some cases, as you will see later, I will assume that IC is equal to IE to do some of my calculations. So what I can see from this formula, beta DC is equal to IC divided by IB. IB is a very small current in comparison with IC, so the value of beta is a large value. And I can see it there in that sentence, they say 20 to 200, depending on the transistor, or even higher. The next sentence is also important, where it says beta DC is usually designated as an equivalent hybrid parameter. You will be introduced to hybrid parameters later in the course as well. And this parameter is called HFE. You can see it's a small h with capital letter subscripts indicating that it is a DC quantity again. And this you will get on the data sheet. You've already discussed the data sheet of a diode. We will also discuss the data sheet of a transistor, but you won't find the quantity beta DC on a data sheet because the manufacturer uses hybrid parameters to do measurements on the transistor to give us this data. So it will be called HFE on a data sheet, but we will see that later. Just underline it and make sure that you take note of that. Alright, that was beta DC. The other ratio that we talk about, the currents, is the ratio of the DC collector current IC to the DC emitter current. That is called DC alpha. So take note, it's the sign of alpha, but the subscript, capital letters again, DC, tells me that it is a DC quantity. Alright, so the formula for alpha DC is IC divided by IE. What do I know about these two currents? IE is the largest, IC is almost the same size as IE, but it differs by the value of IB, which is very small in comparison. So what can I already imagine about the size of alpha DC? Alpha DC will always be less than 1, but it will also be close to 1 because it differs only by IB, that's so small. So that's why at the bottom or just below that formula you can underline this. Typically values of alpha DC ranges from 0.95 to 0.99 or greater, but alpha DC is always less than 1. Always less than 1. Keep that in mind. So if you have to do calculations at some stage, and then that's a way that you can check your answers with. Né? I know that beta DC is a large value. I know that alpha DC is a small value, actually always less than 1, but still very close to 1. But you can have a look there at the example where these values are calculated, which brings me or reminds me about the next point again. Remember to do all your calculations accurately to 3 decimals, and it must always be expressed in engineering notation, especially when we're going to work with very small currents like here you can see microamps and so forth. Né? So if you don't work accurately, you won't even see a difference in the different answers that you're going to calculate or going to work with. So keep that in mind. Alright, so that is DC beta, DC alpha. Please always also remember that these are ratios. A ratio don't have a unit. So you don't write a unit after that. Now it's just a ratio between these two currents for beta DC and for alpha DC. Okay, the transistor DC model. There on the next page. The ideal DC model for an NPN transistor just shows me the currents, current source, and how it acts and so forth. You can find it on the top of page 169. You can view the unsaturated, we can refer back to the book there. You can view the unsaturated Bjt as a device with a current input and a dependent current source in the output circuit, as shown in figure 4.7 for an NPN. The input circuit is a forward bias diode through which there is a base current. The output circuit is a dependent current source, that's the diamond shaped element, with a value that is dependent on the base current, IB, and equal to beta DC times IB. Recall that independent current source symbols have a circular shape, as you've seen earlier in the textbook. But what is important here is that we're going to do the Bjt circuit analysis now. We've already seen there are 3 DC currents, and also we're going to identify the 3 DC voltages. Now, the 3 makes sense because I only have 3 terminals on this device. Now remember, I've got the collector, base, and emitter, and we've already established that I have then at the collector I have the collector current, at the base I have the base current, at the emitter I have the emitter current flowing in directions I've shown, and the largest being IE, which is IB plus IC. Alright, now the voltages. 3 terminals, so what will the voltages be called? Collector voltage is going to be VC. Collector voltage. Voltage at the base, VB. Voltage at the emitter, VE. Please take note again, these are capital letter subscripts, so it indicates DC voltages. If I give you a single subscript letter and you have to do this practically, say I ask you to measure a voltage VC. Of course you have 2 terminals, a red and a black terminal that you have on your multimeter, and you will put it on DC voltage to measure the DC voltage. But if I ask you to measure VC, you're going to measure it with reference to what? If I have a single subscript letter, what do? Of course you will take the red lead and you will put it on the collector. Where will you put the black lead? You always measure with reference to ground. Single subscript, red lead will go on the subscript, which is C in this case. The black lead will go on to the ground. Then I measure the voltage with reference to ground. So that goes for VC, VB, and VE, which I can measure then in that way. Of course, I also have to be able to calculate these voltages, and I also have to be able to calculate the voltages between the terminals. So I also have to be able to calculate VBE. How would I calculate VBE? Actually, we don't calculate VBE, we make an assumption. Remember, base emitter junction, forward biased PN junction, approximately 0.7 volts. Ne? That we know already. So that's an assumption that we make. And in this case, you've done series parallel circuits in electrical engineering 1. Remember I told you I'm looking here at this series circuit. So it is important that I do know my Ohm's laws and Kirchhoff's laws, because I'm going to apply it everywhere in electronics. So you must make sure that you know Ohm's laws and Kirchhoff's laws. Very important. So if I look at the circuit there as indicated at VBB, I've got a resistor RB, and I've got a junction, a base emitter junction. Alright, now we've already seen that I have a voltage drop over the base emitter junction of approximately 0.7 volts. But of course I also will have a voltage drop over RB. Ne? So I can determine a voltage drop over RB, VRB. How would I determine VRB? Ohm's law again. Eh? V is equal to I times R. Then of course I have to know the values of the resistor, and I have to know the value of the current IB to be able to calculate VRB. And normally I would have the value of VBB, so I can calculate VRB by using Kirchhoff's law, for instance, as well. I've seen that I can use Ohm's law. VRB is equal to IBRB. That's one way. But I can also use Kirchhoff's law. What does Kirchhoff's law state? The sum of all the voltage drops around a circuit should be equal to the supply voltage. No. So now I already know what is the voltage drop there over the base emitter. That is 0.7 volts. And say, for instance, I know what is the supply voltage here. Say that is 3 volts. Then I can determine VRB. Then VRB should be equal to the supply voltage minus the VBE, and then I have the volt drop over the base emitter junction there. Alright, in this specific case, if I ask you to go and measure VE, what's the value of VE going to be? Remember how I told you how to measure practically? I will put the red lead on the emitter, and I will put the black lead on ground. What will I measure? Is there any resistance between those 2 points? No resistance, no? When there's no resistance, there's no potential difference, there can be no volt drop. So in this case, VE should be equal to 0. There's no resistance, there's no volt drop, then VE will be equal to 0. Alright, so VB and VBE will be the same, because VB is measured with reference to ground, from base to ground. We've seen that is approximately 0.7 volts. But if I measure VBE, which is, I put the red lead, remember we read from left to right, so VBE, so the red lead goes onto the base, the black lead goes onto the emitter. What will the value be? 0.7, as we already know, né? And VE will be 0. VB, what is VB going to be? With reference to ground, VB and VBE will be exactly the same, because there's no resistance between emitter and ground. So in this case, it's not always true is that VB and VBE will be equal to 0.7, because there's no resistance at the ground. Alright, the same applies for the series circuit on this side. Kirchhoff's laws and Ohm's laws still apply, so I can calculate the voltage drop over RC. What is the voltage drop over RC? By using Ohm's law, IC and RC. V is equal to I times R, so I must have the values of IC and RC. But I can also calculate the same as I've done by calculating VRB by using Kirchhoff's laws. Where do I have voltage drops? I have a voltage drop over RC. I have a voltage drop between VCE, and I've got no voltage drop there, so that's the only 2 voltage drops that I have. So in this case, because there's no resistance there, what is the value of VC? VC, remember I put the red lead on the collector, black lead on ground, measure with reference to ground for a single subscript, as I've seen here. I will get the value, and then I can also measure, of course, VCE. VCE, that's between the collector and the emitter, so the red lead goes on the collector, the black lead goes onto the emitter. Is there going to be a difference between VC and VCE? In this case not, because there's no resistance between emitter and ground. So there's no extra voltage drop. So in this specific case, VC and VCE will be the same thing. So if I apply Kirchhoff's voltage law, then I know the sum of the voltage drops around the circuit should be equal to the supply voltage. So if I want to determine theoretically VC, and in this case also it will also be equal to VCE, it will be the supply VCC minus the voltage drop over RC, VRC, then I have the value of VC or VCE. Okay, so now I see that I could calculate all the voltages. I can even calculate VCB, because now I've already calculated VC and I've calculated VB. So what is going to happen with VCB? VCB, and read from left to right, so VCB is just going to be VC minus VB. Collector base junction, or actually base collector junction. And remember what we always read from left to right. So VCB is going to be VC minus VB. Okay, so VC should be larger than VB. I should get a positive voltage. But remember, I'm talking VCB. And what do I know? VBC is actually the value that I'm looking for, because remember that the base collector junction is reverse biased. So I would most probably ask you, what is the value of VBC? Which of course is VB minus VC. And we've seen that VB is equal to VBE. In this case, it's a small voltage, 0.7 volts. VC will be much larger. Say, for instance, it's 7 volts. But what I'm getting at is this answer will be negative something. Say negative 6.3 volts. What does that indicate? That the base collector junction is reverse biased. Very important, né? So the base emitter junction is forward biased. We've seen that, 0.7 volts. But the base collector junction is reverse biased. It gives me a negative voltage, as you will see later in the calculations that you're going to do. But anyway, let's have a look at what the book says. If we carry on there below that figure that I've just explained everything on. Basically what we've discussed, we've all seen already the equation 4.3. VBE is equivalent to approximately 0.7 volts. That's the assumption that we make, forward biased PN junction. You can underline the sentence just below that just to help you remember that it is not exactly 0.7 volts. I say although in an actual transistor VBE can be as high as 0.9 volts and is dependent on current, we will use 0.7 volts throughout this text in this book. So keep that in mind. Right at the bottom, see there they already mentioned Kirchhoff's law. Kirchhoff's law that you've learned since school, and you've done it in electrical engineering again. You'll do it in electronics again. You will always use Kirchhoff's laws and Ohm's laws in electronics. I can determine that the voltage across RB is VBB minus VBE, as I've explained to you now. Now if we turn the page, also by Ohm's law, I've seen that VRB is equal to IBRB. Then substituting for RB, I can substitute, then it will be IBRB is equal to VBB minus VBE, and then solve for IB. So all that they've done here is they've combined the formulas. IB, and I've combined then Kirchhoff's law on top, VBB minus VBE to determine the voltage drop over VRB, and below the line RB, which gives me my Ohm's law. The voltage at the collector with respect to the grounded emitter, remember VCE. VCE, and in this case, in this specific circuit's case, VCE and VC will be the same thing because there's no resistor at the emitter, so there's no voltage drop. It's going to be the supply, VCC minus VRC, and the voltage drop over RC, Ohm's law, IC times RC, but I can also use Kirchhoff's law. We actually did use Kirchhoff's law. And then the voltage at the collector with respect to the emitter, VCE, which is actually the same as VC, VCC minus ICRC, which is the volt drop over RC. And remember, this is important. We've done that in the previous section. IC is just jiggling of the formula. Remember, beta DC was equal to IC divided by IB. In other words, IC is equal to beta DC times IB. And then lastly, the voltage across the reverse biased collector bias junction, VCB, as we've seen, is VCE minus VBE, but we've also seen that VC E is equal to VC because of no resistor at the emitter, and VBE is also equal to VB because there's no resistor at the emitter, so it will be the same. And then, as I just mentioned it, then scratch it in there right next to it, so if you also want to do that, you're welcome. Alright, then example 4.2, please go and work through that to make sure that you understand this section, where example 4.2 asks determine IB, IC, IE, the three currents, and also VBE, VCE, and VCB. Please note for the VCB, read from left to right. So it's VC, it's going to be VC minus VB. If I ask you to calculate the value of VBC, then it will be VB minus VC. But if you look there at the solution quickly, you will see all the equations that we've just discussed. A combination formula there, IB, VBB minus VBE over RB, IC beta DC times IB, IE is the sum of the two currents, IC plus IB, and so forth. So please just work through that section and make sure that you do understand. Okay, the next thing that I want to discuss here is we're going to draw some collector characteristic curves of the transistor. This is very important that you do know the characteristic curve of the transistor. Always IC against VCE. IC against VCE. Now they do it under certain conditions here, the same as we've done previously with the two voltage supplies. You will see now I still have a voltage supply on the base and I still have a voltage supply on the collector, but it's now two variable voltage supplies to be able to draw this family of curves as indicated here in figure 10. Okay, so firstly you can follow there in the book how they approach this. So firstly, both these power supplies will be adjusted to 0. Then I will start to adjust VBB firstly. So I will increase the value of VBB. What's going to happen? Base emitter junction is going to be forward biased, but because VCC is also equal to 0, the base collector junction is also going to be forward biased. So this is not the condition for amplifier at this stage, it's just to be able to draw this characteristic curve. So what happens at that stage, because both these junctions are forward biased, the transistor goes into saturation. We will discuss that also a bit later. So what will happen as I increase VBE, VCE is going to increase. You can see that I have a curve here of IC against the VCE. So as I increase, here you can see are my different IB currents. Of course, IB is going to increase as I increase VBB. So as I increase IB, I see that IC will also increase and VCE will also increase. Because remember, the formula that we looked at is that IC, it's actually the ratio of beta, the ratio between IC and IB. So IC is going to be equal to beta DC times IB. So if I increase VBB, IB actually also increases, and as IB increases, of course IC increases, and I can see it here on the curve. Remember, this is IC against VCE. So as IB increases, I can see that my IC increases and my VCE also increases up to a certain point. There you can see it increases up to between points A and B. And look here, what happens here? As soon as the value of VCE becomes approximately 0.7, I can see that my current now flattens. So what's going to happen now? The base collector junction now becomes reverse biased. Alright, then the current between points B and C stays basically constant. There's a slow rise in it because of some leakage currents. When I will reach point C, where the transistor should never be operated, actually it goes into breakdown, and you can see there's a huge increase in current. So I don't actually operate the transistor in that region. But also in the curve here on the right hand side, the C part of this figure, I can see then for different IBs, every time that I change the value of IB, I will get a different value of IC. Okay, so I bias by using VBB, which will increase IB, and as IB increases, I will get a different value of IC in each case, as I can see on this family of curves here. But it will only go up to a point which is called the saturation point, which we will discuss just now. So that IC will increase. Another point is, of course, when I can see also here when IB is equal to 0, remember here 0, if there is no IB, then of course IC will also not be will also be equal to 0. Now, so if IB is 0, of course IC will also be equal to 0, and I can see that the transistor will be switched off, which we will call cut off. But it is discussed there in your textbooks. You can read through it there. It starts there on page 171. And I've marked it there on the next page. As it carries on, say when both junctions are forward biased, the transistor is in the saturation region of its operation. Of course, saturation is a state of a Bjt in which the collector current has reached the maximum and is independent of the base current. We will discuss that in detail also later to make sure that you understand. As VCC then is increased, VCE increases. Of course, now I also increase that voltage, so VCE as VCE increases at the collector up to this point where it reaches 0.7 volt due to the VCC increase because VCE remains less than 0.7 due to the forward biased base collector junction. Ideally, when VCE exceeds 0.7 volt, the base collector junction becomes reverse biased and the transistor goes into the active or the linear region of its operation. Linear region of the operation means that is the area where I'm going to use the transistor for amplification. As you can imagine for yourselves, when IB is equal to 0, in other words the transistor is off, or it goes into maximum current, it's in saturation. Those are the two areas I will use it as a switch. So it's either in cutoff and saturation, the switch is off or the switch is on, or in the area in between I will use it for amplification, which is called the linear region, but we will discuss that in much detail as we go along. Alright, so once the base collector junction is reverse biased, IC levels off and remains essentially constant for a given value of IB as VCE continues to increase. Alright, actually IC increases very slightly as VC increases due to the widening of the base collector depletion region. That's why that line is not completely horizontal. Nah. Alright, this results in fewer holes for recombination in the base region, which is effectively causes a slight increase in beta DC. This is shown by the portion of the characteristic curve between points B and C, where it's not completely horizontal. For this portion of the the characteristic curve, the value of IC is determined only by the relationship expressed as IC is equal to beta DC IB, as we've seen here. Nah? Then this formula is true. Alright? For that portion between B and C. Sorry. Yeah, between points B and C, my formula of IC is equal to beta DC then remains true. Alright, when VCE reaches a sufficient high voltage, the reverse bias base collector junction goes into breakdown and the collector current increases rapidly, as we've seen here, and this is the area where the transistor should not be used. Now then it goes into breakdown, burns out, doesn't work anymore. Alright, then lastly here it says when IB is equal to 0, the transistor is in cutoff. That's where I said cutoff is where the switch is actually off. Actually, they say there's a very small collector leakage current, but it's so small that we ignore it. Alright, so this is the way that I will draw the transistors or the transistor characteristic curve. And there's a whole family here in the C section. But it's important to see here that the current IC will increase up to a maximum point. This maximum point will be determined by the circuit, as we will see. then the current will remain basically constant up to a point, and the device will break down where it will not work anymore. But have a look at example 4.3, where they ask you to sketch an ideal family of collector curves for the circuit in figure 411 for IB is equal to 5 microamps to 25 microamps in 5 microamp increments. Assume a beta DC of 100 and that VCE does not exceed breakdown. So if we quickly look at the solution there, you can see then that here's the family of curves, and I can see then it's done in steps of IB 5, 10 microamps and so forth, and that I have my IC's currents accordingly, as you will calculate because you have the formula which says IC is equal to beta times IB. The values of IB are given, so I can calculate the values of IC to be able to draw this curve. Alright, while we in the textbook here, they discuss on page 173 cutoff. As previously mentioned, when IB is equal to 0, the transistor is in the cutoff region of its operation. Now, this is important. Let me just go back here. That I know the parameters of cutoff and saturation, but let's talk about cutoff first. I just want to clean up here a bit. Let's just clean this characteristic curve of the transistor here. For IC against VCE. Alright, now we've seen for different IBs, I will get different values of IC. But I've seen that if the IB is equal to 0, IB is equal to 0, then of course IC will also be equal to 0. No. So that's one of the parameters. Let's say the parameters for cutoff. When a transistor is in cutoff, what are the parameters? The parameters are IC and VCE. That's what my curve is about. No? I've got IC against VCE. So when I'm talking cutoff, what is the value of IC? I can see according to my formula, IB equal to 0, beta times 0 is going to be 0, so IC is also going to be 0 amps. No? What is the value of VCE going to be? If IB is equal to 0, what's going to happen to this transistor circuit? Let me just clean the circuit here up as well. Remember now, I said that the transistor can be used as a switch or for amplification. Now we're looking at it as basically as a switch. Né? And we've seen that I'm looking at this part of the series circuit. Here's my transistor. So let's use it as a switch. We will discuss it again a bit later. Now it is in cutoff. In other words, the switch is open. Eh? So there's my switch. We've seen now that the value then of IC is going to be equal to 0. What's the value of VCE? That's between the collector and the emitter. If that switch is open, if that is an open switch, what will it be equal to? The same as we did with the diode that you've done. When the diode is reverse biased, what do I actually measure? I measure the supply voltage. What is the supply voltage in this series circuit? It's equal to VCC. No? Those are the parameters for cutoff, and I can plot it here basically on this curve. You can see that IC is equal to 0. VC is going to be equal to VCC. We will discuss it a bit later again. Alright, so when the switch is going to be on, now the switch is fully on. I've got my formula, IC is equal to beta DC times IB. Now I start to increase IB. Remember it was 0. Now I increase IB. As I increase IB, IC becomes more and more and more up to a certain point, né? Where I get maximum current. The maximum current is called the saturation current, IC sat. Maximum current flows through this device. So IC, the parameters for the transistor as a closed switch. So here's the parameters IC and VC. What is IC going to be? It's going to be equal to the maximum current, which is IC sat. We'll discuss it again. But what is the value of VCE going to be? Remember now, as IC increases, what's the value of VCE going to be? Remember now, it's a closed switch. What is the voltage drop over a closed switch? What was the voltage drop over the closed switch of the diode? When the diode was switched, a closed switch actually ideally should give me 0 volts. There should be no volt drop. Now, what we've seen, a forward bias diode gives me a volt drop of approximately 0.7 volts because it's not an ideal device. Now, the same happens for the transistor. The voltage is a bit different though. It's not going to be 0.7 volts because we're talking about 2 p-n junctions. You will see in this book, but I will mention it again. It should be 0. Closed switch should be 0. So VCE should be 0. But because it's not an ideal device, we will assume, unless otherwise mentioned, that it will be approximately 0.2 volts. So those are the parameters for saturation, and those are the parameters for cutoff. But yeah, I will show it to you again in the book. So I can go and plot. So it's not going to be exactly 0. This is the ideal point for saturation. IC is equal to IC sat. You can see the current is not 0. It's the maximum current. And VCE is equal to approximately 0, actually 0.2 volts. Anyway, discussed here in the book. You can just mark it there in the books again. So I wrote there next to it, the parameters will be equal to IC is equal to 0 amps, and VCE will be equal to VCC, whatever the value may be. When it isn't cut off, it acts like an open switch. The saturation part there is when the base emitter junction becomes forward biased and the base current is increased, the collector current also increases. We know the formula, IC is equal to beta DC times IB, and VCE decreases as a result of more drop across the collector resistor. VCE is equal to VCC minus ICRC, as we've seen in the previous section. When VCE reaches its saturation value, VCE sat, the base collector junction becomes forward biased and IC can increase no further, even with a continued increase in IB. I will point it out again later. At the point of saturation, the relation, and this is important, underline it. At the point of saturation, the relation IC is equal to beta DC times IB is no longer valid. I can increase IB as much as I like. IC cannot increase anymore because of the limitations of my circuit. Alright, so VCE sat for a transistor occurs somewhere below the knee of the collector curves and is usually only a few tenths of a volt, approximately 0.2 volts, as I've written here next to it. So remember again here, Kirchhoff's law, VCE sat, approximately 0.2 volt. So the parameters here for saturation is IC is going to be equal to IC sat, and VCE is going to be equal to VCE sat, which is approximately 0.2 volts. Alright, then the DC load line. The DC load line, now we've established, let's just go to our board here again. Here's the family of curves. There it is. Remember now we've applied different IBs. Remember these are all different IBs. As I increase IB, say 5 microamps, 10 microamps, 20 and so forth. And as I increase IB, I can see also that IC increases because of my formula. IC is equal to beta DC times IB. Alright, and as we've seen, only up to a point, which is the saturation point. Now here, this one is a bit more accurate. I can see when it is my parameters for saturation. IC is going to be equal to IC sat, but VCE sat is a few millivolts, 0.2 volts approximately. We make the assumption. So yeah, I've seen, and as we've already seen, I've drawn my saturation point I've drawn my cutoff point. You can see here cutoff IB is equal to 0. VCE is equal to VCC. That is for cutoff. Saturation, IC sat, and VCE sat, which is approximately 0,2. But you can see here, if I connect these 2 points, that is called the DC load line. So the transistor being used as a switch there and there. The transistor being used as an amplifier between cutoff and saturation. That area in between there, I will use for linear amplification. Alright? But we can read it there in the book again. If you refer back to the textbook, you can see the DC load line. The bottom of the load line is at ideal cutoff where IC is equal to 0 and VCE is equal to VCC. The top of the load line is at saturation where IC is equal to IC sat and VCE is equal to VCE sat, which is approximately 0,2 volts. And in between cutoff and saturation along the load line is the active region of the transistor's operation. We will discuss the load line in more detail in the next chapter, but you have to be sure that you understand the transistor being used normally as a switch and as an amplifier. So the switch you can see, cutoff saturation, in between those two are the linear region, is the linear region where I will use it for amplification. Just understand that so far. We will discuss it in more detail as we go along. Alright, we've already discussed beta, but I want to discuss more about beta, give you some more information about beta, and I also want you to mark some very important sections in the textbook. So if we go look at figure 417, variation of beta DC with IC and several temperatures. So already I can see just by looking at this curve, I can see that I have a curve of my beta DC against a change in collector current and also in a change in temperatures. So I can already see by looking at this curve that beta DC is not a constant value. It is influenced by changes in temperature and it's also influenced by changes in collector current. And here I can see, let's take a transistor that has to operate at what we call room temperature. There is 25 degrees. And let's say that the collector current at this stage is 10 milliamps. So if I go and look at 10 milliamps at 25 degrees, I will see that my beta DC value is approximately, I would say 37. But you can also see if the temperature increases and the current remains at 10, let's go up to 125 degrees, what is the value of beta now? I can see that the beta value now becomes about 58. So I can see very clearly that temperature influences my value of beta DC. And also I can see, even if when I change, say the temperature remains constant at 25 degrees Celsius, but IC changes. Let's say IC changes from 10 milliamps to 1 milliamp. You can see what happens to the curve here. It goes from approximately 37 down to, I would say, about 25. That's when the temperature decreases. If the temperature if IC decreases, if IC increases, I can see the same thing happening. Say IC increases, and you can see it gets worse as it gets higher. At 200 milliamps, it becomes approximately 16, 17. Alright, so very surely I can see beta DC is not a constant. Constant value doesn't remain constant. It changes with temperature, and it also changes with changes in collector current. Now we've seen that beta DC is actually a ratio between collector current and base current. And so I have this parameter for each transistor. So each transistor that I have, manufacturer will measure this. Remember, we talked about hybrid parameters. The H parameter is actually called HFE. But what is important is to always remember, and I will show you in the textbooks just now, is that even though beta DC changes with conditions as IC changes or temperature changes, you are 100 students sitting here and you will all get the same type number of transistor, but there will not be two transistors that's got the same beta value. That is something that the manufacturer cannot control, and that's what I want you to mark here in your textbooks. Alright, so on this section where it says more about beta DC, we've seen there firstly that beta DC is not a truly constant but varies both with collector current and with temperature, as we've seen in the graph. But I want you to mark this paragraph here at the bottom of page 175, just below figure 417. A transistor data sheet usually specifies beta DC, remember HFE on the data sheet, at specific IC values. Even at fixed values of IC and temperature, beta DC varies from one device to another for a given type of transistor due to inconsistencies in the manufacturing process that are unavoidable. Important. We will see later when we discuss amplifier circuits, biasing circuits. Why is it important? Because this beta, of course, as you can imagine, features highly in amplifiers. The beta DC specified at a certain value of IC is usually the minimum value. Beta DC min, although the maximum and typical values are always sometimes specified. It's not even always specified, but we will see it when we discuss the transistors data sheet as well. Okay, another thing that's important on page 176 is maximum transistor ratings. You've learned this with the diode as well, and I suppose with other devices, resistors and whatever that you've done in electrical engineering, is that there's a maximum rating for each device. It cannot handle all the current or voltage that you apply to it. There are limitations. Problem normally, or not normally, actually the problem is heat dissipation. The device gets too hot and eventually it burns out. It can't get rid of the heat fast enough. That's why you've seen with the resistors, the higher the wattage of the resistor, the bigger the resistor is. The bigger the surface area, the quicker it can get rid of the heat. So it can handle more wattage. But anyway, I want you to mark this. A Bjt, like any other electronic device, has limitations on its operation. These limitations are stated in the form of maximum ratings and are normally specified on your manufacturer's data sheet. I will point it out to you again. Very important, and we're going to do some problems that also will address this. Typically, maximum ratings are given for collector to base voltage, collector emitter voltage, emitter to base, collector current, and very importantly, of course, power dissipation. The product of VCE and IC must not exceed the maximum power dissipation. But of course, both VCE and IC cannot be maximum at the same time. If you recall the characteristic curve that I have of IC against VCE and the load line, so as I move up and down on the load line, I can imagine if I move closer to 0, then you can see that IC will be less, but VCE will be less, but IC will increase. And if I move down on the load line, you can see that my IC will become less, but VC will increase. So they cannot be both high at the same time. That's all that they're saying here. Alright, so if VCE is maximum, then IC can be calculated as in the formula there, PD max divided by VCE. PD max I can get from the data sheet. I will show you. If IC is maximum, VCE can be calculated by rearranging the previous equation. VCE then will be PD max divided by IC. But there's an example there at the bottom of the page also showing you in figure 418. For any given transistor, a maximum power dissipation curve can be plotted on the collector characteristic curves as shown in figure 418a. These values are tabulated in figure 418b. Assume that PD max is 500 milliwatts. This I will get from the data sheet. VCE max is 20 volts. I will get it from the data sheet. IC max is 50 milliamps. I will get it from the data sheet. The curve shows that this particular transistor cannot be operated in the shaded portion of the graph. IC max is the limiting rating between points A and B. PD max is the limiting ratings between B and C. And of course, VCE is the limiting rating between points C and D. So have a look at that graph, and then, of course, example 4.5 and 4.6. Important to work through that and make sure that you understand how to determine the maximum transistor ratings, power dissipation, and so forth. First one there, example 4.5 specifically, a certain transistor is to be operated with a VCE is equal to 6 volts. If its maximum power rating is 250 millivolts, what is the most collector current that it can handle? Then of course I just apply the formula that I've seen at the top of the page. Example 4.6, however, transistor in figure 419 has the following maximum ratings. It's given to you in this stage. Sometimes it's given. In some cases you will be given a copy of a partial data sheet, and you must find the values on the data sheet yourselves to do the calculation. So you have to be sure to make how to make use of the data sheet as well. Right, PD max is 800 milliwatts, VCE max is 15 volts, IC max is 100 milliamps. Determine the maximum value to which VCC can be adjusted without exceeding a rating, and which rating would be exceeded first. Alright, so if I go and look at this solution, first I have to find IB so that I can determine IC. I've already seen how to determine IB with a combination of Kirchhoff's laws and Ohm's laws. So IB in this case 195 microamps. Then I can calculate IC by using my beta DC formula, the ratio between the two currents. IC is then 19,5. Then I can see IC is much less than IC max. I don't know what happened. Everything else is do it.